Okay. Good morning. Thank you all for attending. So my name is Jeff Catlin from Edgecore Networks, and this morning I'm just going to go over a few of the updates that we've been doing on the access products for the telco group. Oops. So kind of the agenda is I'll go over a couple of the specifications at a high level, just one slide on each that led to the recent product contributions that we've done for a couple products. I'll go over one slide, a couple slides on a new contribution and an overview of that and what that product is, and then just touch upon community collaboration. So the first product that I'm going to talk about here is based on a specification. So for those of you that were here a year ago, Deutsche Telekom put through a specification for an open GPON OLT that specified two variants of a OLT, a 64-port variant and a 32-port variant of a GPON OLT. It specified a central office type or temperature-controlled environment, so it wasn't a outside plant type of specification, so temperatures were 0 to 40. And that specification suggested on types of silicon that could be used in that OLT, which was the Broadcom Qumran AX ASIC for the switching silicon and the Broadcom Maple SoC for the PON MAC. And that is shown here on this slide. This is out of the DT specification, a high level of block diagram of what that product might look like. So my company, Edgecore Networks, followed through on that specification and developed a product. And that product is, we have it here, we're showing it here today. And that's out for software support and POC testing now. This is the 64-port variant based on that specification from Deutsche Telekom. A 32-port variant can be obtained from this by just depopulating certain ports because it's a single PCB board with ports on either side. So to get the 32-port version, we depopulate all the ports on either the top or the bottom side, whatever is the best for the cooling. So again, this is shown here, 64 ports of GPON through SFP connections, 2 ports of 100 gig for uplinks, and also 8 ports of SFP 25 gig for uplinks. So either 100 gig or 25 gig uplinks, depending on the cost of the optics and how the backhaul plant is laid out. Also included is the standard, RJ45 management and console port and a USB port. This also accepts a optional BMC module. This ships by default today with the BMC module. And it has support for different network operating systems. So the first network operating system that's supported on this is the ONF Volta/SIBA suite of software, which was talked about earlier today. So that's supported on this. Also, there's an announcement or a presentation later today. There's a commercial NOS offering going to be offered on this as well. So now we'll have the white box OLTs kind of following the same path as the white box switches, where there's open source software offerings and then there's commercial NOS offerings as well. So there'll be a commercial traditional OLT option on this as well, where the OMCI and all the protocols that you would expect from an OLT actually reside inside the box. And that presentation's at 2:30 for people that are interested in the networking track. Okay, and so this is a contribution that we've completed. This product just received OCP accepted status as of, I believe, last week. So our contributions, as in all of our contributions from Edgecore, include these components up here. So there's a hardware design package that includes everything from schematic and the board files, mechanical files, and a test plan, bill of materials. All that stuff is available for public review. And the software components over here on the right-hand side of the slide are things we provide also. So, of course, it's the ONI installer, Open Network Linux. We support the OCP baseline Redfish profile, so that's supported in either one of two ways, either on the BMC, or if the BMC is not there, it's supported on the x86 CPU for management of the low-level hardware primitives. We support the Open Optical Monitoring API that was done in OCP networking group, so it's a way to gather the low-level information out of your pluggables, such as inventory control, launch power, and the stuff of that. All that kind of information is taken out of the EEPROM on the pluggables and exposed through an API. That's what the Open Optical Monitoring API is. And of course, it supports the Open OLT driver for use in a ONF SIBA type environment. And all those components, software components, are open source as well. So everything shown on this slide is part of the contribution, and it's all open source at this point, hardware and software. Second product that we're going to talk about, last year at this time, Edgecore put through a specification for what we called an aggregation router in a telco environment. So there was two variants of this, a 40 port and an 80 port, and the high level requirements were, NEBS 3, modular CPU, BMC support, and the appropriate silicon used for telco type environments, carrier environments, which was Jericho 2 silicon. So based on that specification, we did get some feedback, not much from the community, unfortunately, but some. The feedback we got, we incorporated into the design, and that resulted in this product here, which again is unfortunately not shown here, excuse me, but we are shipping this to software partners. This is 3RU, excuse me, based on dust fans we have on here for NEBS requirements. So they have removable dust filters on this. It's NEBS level 3 compliant, 0 to 55 degrees C. It supports the Jericho 2 silicon. We also support the expandable TCAM and statistics options. So the OP2, if you're familiar with Broadcom silicon terminology, can support extended TCAM and ACL functions, as well as advanced statistical gathering. So we've connected the OP2 up so it can perform both of those functions. We can also produce this SKU without the OP2 for cost savings if that's not needed. So this here is a 2 PCB board design with the CPU and 40 ports of connectivity on the main board, and the top board just carries the second Jericho 2 and reverse gearboxes. This is much like the previous submission, includes all of the same hardware files and all of the same software components that are open source and is part of the contribution. Again, this is the 80 port design. The 40 port design can be obtained from this same architecture just by removing the top daughter card and redoing the sheet metal for lesser RU. Okay, so we'll follow up both of these contributions with the lesser port variants of the OLT and also the aggregation router. And this is, again, same timeline as the OLT, as this is now OCP accepted as well as of last week. So both of these contributions now have gone through the process and they're OCP accepted. So if you were here yesterday and caught some of the keynotes, Bill Carter went over some of the collaboration that's going on between the different open source communities. And so one of the things that we worked with OCP and TIP is we're starting to cross-pollinate or co-contribute designs between the two communities. So what Bill kind of went over yesterday is we have, this is our version of a cell site router based on AT&T specification from last year. There's a couple versions of this router in OCP from different vendors. This is Edgecore's. So what we've done is we've taken our specification and design files and repackaged all of that information up and contributed that to the Telecom Infra Project, or TIP. So that's a different open source community Some of the same vendors like us participate in both communities. Some of the same carriers or telco operators participate in both. However, some do not. So there's a certain set of operators that only participate in TIP and a certain amount of operators that only participate in OCP. So we're hoping that by these contributions we do between the communities, we'll start to bring more customers, more users, and adoption of open networking in general to the public. So this was the announcement yesterday, and that contribution was done a couple of weeks ago into TIP. So now that product there is an OCP accepted product, but also is a TIP accepted product and now available to the TIP members in that community and the software partners and the likes of that. So following that, what we have done also, and we're kind of announcing it here at this meeting, is we've taken a cell site gateway that was previously specified in TIP and contributed to TIP by the company I work for, Edgecore, and now we've taken that design package and that specification, we've packaged that all up, and now we've contributed that to OCP. Okay, so now we've gone both ways with those contributions. One went from OCP to TIP. This one goes from TIP to OCP. And it's very similar to the other cell site gateway that I just went over, but there are some differences. And we'll go over those. So in TIP terminology, they're called disaggregated cell site gateways, or DCSGs. In OCP terminology, they're called cell site routers. So just kind of different terminology, but the products really do the same thing. So what does this contribution and product actually look like? Okay, so looking at a block diagram, again, it's very similar to the original OCP version in that it uses the same packet forwarding machine. It's a Broadcom Qumran AX chipset. Okay, it has an x86 CPU card. In this design, it's a COM Express Type 7 CPU card, whereas in the other one, it was a Edgecore standard CPU card design. So this is more of a standard, I guess you'd call it a standard commodity CPU card design in it. Again, it has a timing design that's very similar but not exact, and we'll go over some of the differences between the two cell site gateways. Supports removable power supplies and fan tray and the likes of that stuff. A front panel view of this does start to reveal actually some of the differences in this design. So the fan tray in this design is accessible from the front, whereas in the original design, or the OCP type design, that fans were accessible only from the rear. So now in this design, everything is accessible from the front. The only thing on the back is a grounding lug in this type of design. And you start to see different types of ports here that are offered. So we have some ports on this that are called stacking ports. So you have a stack sync port, a stack control port, and you have 100 gigabit ports that are labeled as stacking. And does this have a pointer on it? Yes, okay. So those stacking control and stack sync ports are over here. So there's ports that carry information from the timing circuits from one device to another. And there's also a stack control port that carries information from the CPU of one device to another if you were to stack two of these together. And then these 100 gig ports over here on the right are used for stacking the data between the two devices. These 100 gig ports here, if you're not using these devices as two stacked together, can be used as standard 100 gig interfaces. Okay, so the stacking support on this is really specific to the NOS you're using, whether it supports it or not. But the reason for stacking isn't so much to get a device that's twice as big so you can have twice as many connections to different things. It's more used for things that really require redundancy in case a unit needs to be taken out of service. There's dual connections to whatever your cellular equipment is on the other end of this, is why the stacking support was put into this design. Okay. So this slide, all these slides are available online, so you guys can go back and look at them. But this, I try to just list some of the differences here. Of course, the stacking is different support. There is a different number of 100 gig ports. There's 3 on this design as opposed to 2 on the original design. CPU is different. It's a different modular card, and there's a different CPU. So the original OCP version was a high-end Xeon processor, 8-core. This one is more of a cost-conscious 4-core Atom processor. It's a Denverton processor in the Atom family. One of the main differences here is the airflow. So the original design in OCP was front-to-back airflow. This design is side-to-side airflow. So there are many situations in the world for cell site gateways and backhaul equipment that have to have side-to-side airflow based on the cabinets they're deployed in. So that's a major difference in this is the airflow direction. And then there's some other differences underneath in the types of timing input and output ports that are available or not available. This new design has an alarm port on it for dry contacts that's normally included on telco type equipment where the original design does not. Original design had a BMC or the option for a BMC. This design does not support a BMC. And again, all items on this are located on the front. So fans, power supplies, everything is accessible for the front. Based on being space conscious for different areas in the world that this would be required in. So I think that's the last slide on that. So before I get onto this, so that's kind of the cross collaboration or pollination between OCP and TIP that's going on, and hopefully we'll see more of this with different products for different use cases that help actually strengthen, I think, both communities and offer the different products that are developed in different software pieces and different use cases to be enjoyed by both open communities. So I think that's really positive going forward that we see more of that. And one other thing I just wanted to show here is it's not only TIP and OCP, it's ONF that we heard from in the beginning. So there's 3 communities that we're starting to bring together and share designs and software to make complete solutions. And this kind of just shows one of the products from my company that we're actually combining even another portion of the open source ecosystem to try to help push all this open networking forward. So this is a product, a packet transponder that we contributed to TIP. So the hardware is into TIP. A lot of the software that runs on this comes from OCP. So it supports ONI, ONL, supports Sonic, and then has a interface in conjunction with that talks to a controller from ONF that controls the coherent optical ports, and it has a BMC and a Redfish implementation that can reside on the x86 that's from the OpenBMC community. So we start to see products now that become very advanced as far as coherent packet transponders and the likes of those things that start to incorporate functions from multiple communities to bring together a complete solution to market for use cases. So I just wanted to highlight that hopefully we'll see more of that going on to kind of strengthen all of our communities and help service the customer base better. So that's all I had. And my call to action is, if you're a vendor or operator and you're not currently participating in OCP and specifically the telco work group, please join us and get involved. There's plenty of work to do and still plenty of interesting projects going forward. If you're a consumer of products, buy your products online or through the OCP marketplace. So all the products that are OCP accepted are available on the OCP marketplace website. So that's a good place to go if you're a consumer and look for products, and you can sort on them based on the type of NOS that's supported. I think you'll be able to start filtering on types of silicon and vendor and the different ways to sort all the products up there. And if you currently are engaged in OCP, you can get engaged in additional OCP work groups because there's plenty of work within OCP, or think about getting engaged in one of the other open communities that I've shown here, because although, we're a very active community with an OCP, sharing between these other communities really makes our community stronger and their community stronger, and helps propel the open networking even further with adoption. So if there is any Q&A? No? Okay, well, thank you.